Okay, so now it's my great pleasure to introduce to you our keynote speaker, Zeynep Akata. Hi, now we can see you. Great.
Hello.
Zeynep is a professor for computer science at TU Munich, also director of the Institute for Explainable Machine Learning at Helmholtz Munich. And she has a very successful scientific career behind herself already. She worked as a postdoc with Bernd Schiele at MPI for informatics. She also worked as a postdoc with Trevor Darrell at UC Berkeley. And then became assistant professor in Amsterdam with Max Welling. Afterwards went to Tübingen, where she became professor for computer science at the University of Tübingen, and she was also senior researcher at the MPI for intelligent systems. She has received plenty of awards. Let me name some of them. So it's the Lise Meitner Award, it's an ERC starting grant, it's a German Pattern Recognition Award, it's the Alfred Krupp Award, and so on. Her research interests include multimodal learning with foundational vision and language models, as well as explainable AI, and today she is going to be talking about interpretable vision and language models. So the stage is yours. Thank you very much for joining us.
Hello. It's a pleasure to be here. Unfortunately, I couldn't be there with you in person today, but I hope to visit at some point, and maybe it won't be in this beautiful building at that time, but hopefully soon I will have the pleasure to be there in person. I see that we have a big crowd. I hope my talk is going to meet your expectations. I will share my screen. 1 second. Do you see the slides? Okay, you can. I think I can see that you can. Okay. So my talk is going to be about interpretable vision and language assistants. As mentioned, I'm a professor at the Computer Science Department of Technical University of Munich, and I'm also a part of Helmholtz Munich. So the outline of my talk is as follows. I will first talk about how explanation and learning, in my view, are related. And then I will talk about, I will define what is an explanation. There are many different definitions of an explanation, but some abstract definition. And based on that definition, I will talk about how we can use these kind of explanations in a conversation. Then I will talk about how we do research on tailoring explanations to the communication partner. I believe that this is an important aspect of an explanation. We always think about an explanation as an exchange process, exchange of information, and in every kind of dialogue, the opinion or the view of the communication partner is important. And then I will talk about some future research possibilities. Let's start with explanation and learning. I really like this example because it's in a very, very simple way tells everything about what I think is the most important aspect of an explanation. This is from a Trends in Cognitive Science article written by Tanya Lombroso in 2016, and she creates this two-class classification problem, where we need to distinguish between two different alien species. One of them is called glorp, and the other one is called drent. And as you can see, there are different, these aliens have different properties, like their heads have a different shape, their bodies have a different shape, they have different colors, and so on. And based on some criteria, we are going to create a classifier that hopefully splits these aliens in two equal clusters. we might cluster them according to the head shape, and then we look at the results of the classifier, and we see that it's a 75%, it has 75% accuracy, which is not bad actually, but the big problem is not the accuracy, but we are doing this decision based on the wrong reason. Now this classifier is not generalizable. We go back to the learning problem again and try to see what unique properties define these species. And in fact, there are multiple, but one that attracted my attention is the shapes of the feet. So if the alien has a pointy feet, then it is called glorp. If it has flat feet, it's called drent. So the classifier, it doesn't only classify these objects in the correct clusters, but also it makes the decision based on the correct reason. And this is the most important aspect. So based on this simple definition, what is an explanation? An explanation is an object that is broad, simple, and contrastive. Broad means explanations need to justify a broad range of observations. They need to be simple because we don't know, while we are generating the explanation, we don't necessarily know for which purpose they are going to be used. So if we can afford to create a simple explanation, that would be the best. Then also, according to Tanya's definition, explanations need also be contrastive. So using these explanations, we need to be able to differentiate two alternative decisions. We need to be able to say, according to my explanation, the aliens with pointy feet are glorps and flat feet are drents. So the aliens which don't have flat feet are glorps. In this manner, the explanation needs to be contrastive. Now, of course, these are very discrete and simplistic explanations. If we want to generate more complex explanations, we need a more complex tool. And this could be language. And we also thought, when we started doing the research on vision language based explanations, we thought explaining everything is not necessary or meaningful. If I'm trying to explain the difference between a pen and a bottle, I can say many, many different things, and because they are very different objects. So an explanation is meaningful also when the objects are very visually similar to each other, and it is not easy to distinguish between them based on the first random thing that we can see in the image. So that's why we chose as data sets birds and flowers, fine-grained visual classification data sets, and we asked novice users to tell us what are the interesting properties that they thought are interesting about these objects. And we collected these approximately 10-word long sentences from Amazon Mechanical Turk from subjects who don't know who are not experts of birds or flowers. But nevertheless, they came up with very distinct sentences, especially because we annotated 10 sentences per image. This turned out to be quite useful at least for the purposes of classification. On the one hand, we had attributes that are annotated by experts, somebody who says that these different properties, like the shape of the beak or something, is important about this species, to recognize these species. And another person says, okay, the shape of the beak of this bird is this. Then you can create a vectorial representation of these explanations and use them as side information for classification. And compared to extracting features from these sentences, sentences worked better. So this tells us that the sentences have enough information to be classified correctly. So based on the previous definition, I would like to once more put the concept of explanation into context, in the context of bird classification in this case. So we care about image relevance and image class relevance. We define that a description, an image description is highly image relevant, but not that class relevant. What does it mean? We have two example images from two different classes, and the description says this is a large bird with a white neck and a black back in the water. And the other one says this is a large bird with a white neck and a black back in the water. So the definition of the description between two different bird species could be exactly the same, because in essence, these, if you want to describe the entire image, then these two images share a lot of properties. Then, what is a definition? Definition now is completely class relevant. So it is relevant to all of the properties of the class, but it doesn't have any image relevance. What does it mean? So this, to be able to distinguish Western grebes and lice and albatrosses, we need to look at their yellow pointy beaks, white necks, and the black back. We need to look at the, for example, hooked yellow beak, and maybe we need to look at their feet or something. But not all of the, it is not relevant that these properties appear in the image. These properties, these definitions are going to be the same for any image of the class. A visual explanation, on the other hand, needs to contain both of the properties. They need to be tailored to the class. So they need to talk about the most important properties of the class, but they also need to talk about what is visible in the image, because they need to be tied to the input. So that's where the explanation of these two classes differ significantly, because now we can see that their beaks are different, the eyes of the color of the eyes might be different, and those are also the visible properties. So when we want to generate a text-based explanation, we would like to generate something that is image relevant and class relevant. Now, let's go into how we did that in the past. Let's say our aim is to achieve a dialogue between a user and the machine. The user might look at an image and ask any type of question about this image, and the model should be able to understand the question and answer it correctly. Now, what type of bird is this? Could be a valid answer could be just it's a cardinal, but we don't only want that. We also want the model to be able to justify why it came to this conclusion. And we don't only want it to say because it's the red bird with a red beak and a black face, but we also want it to point to the evidence for these properties. So the sentence needs to be generated in such a way that the evidence needs to be tractable and convincible by the user. So we also saw in the first example that an explanation needs to be contrastive. In this context, the user might ask, why not a vermilion flycatcher? Then the model needs to think about how a vermilion flycatcher looks like, what are the differences between these two bird species, and what is the property that is governed by the alternative class, but not visible in the original image. So it's not a vermilion flycatcher because it doesn't have black wings, and something else could have been mentioned here too. Just it needed to be visible in the image. So this is by now an ancient paper, but the first one where somebody even talked about a visual explanation. So what we did there was we took an image classifier, like a ResNet model, that could take an image and that could give us an image feature and a class decision. So we take that image feature and the class decision, and we feed that as a conditioning variable to a language model that was an LSTM. that is conditioned on these properties. Now, the conditioned on these properties, the next sentence, the next words need to be generated based on this information. So in a way, the sentence that is generated is not a direct explanation of the decision maker, because we don't go into the details of how the thought process of the decision maker was made, but instead we have an post hoc explainer that is trying to achieve all the properties of the explanation that we were aiming for, and based on the visual input. So the sentence that gets generated is may look like this. This red bird has a red beak and a black face. Then we have a part of speech tagger that we call attribute chunker that takes this sentence and divides into noun phrases, and an explanation grounder that is trained on a different task, because this data set didn't have bounding box annotations, could give us a prediction of what would be the bounding boxes that correspond to these, the most highly likely bounding boxes that correspond to these properties. Then for alternative sentences, we could do the exact same process. And then in the end, we have a ranker, a sentence ranker that we call phrase critic, that computes the cumulative score of all the noun, phrase, and bounding box correspondences to decide on which sentence would be the best suiting for that image. So assuming that our model is able to generate class-specific sentences, this extra mile was done for making these sentences more image-specific. So I can show you some examples. This is the red-winged blackbird because is a template that we used at the time. The red-winged blackbird is in this case correctly predicted class, and this is the sentence that gets generated, and these are the bounding boxes that appear on the image. And although the explanation generator in these two examples is exactly the same, this sentence gets chosen by the phrase critic model because it has a higher cumulative score for bounding boxes and noun phrases combination. And by constraining the generation in this way, we also see that the generated sentences become also, although this wasn't the goal, more class specific. And so another goal was to generate counterfactual or contrastive explanations. Here we have a semi-automated process where we can generate the first half of the sentence and then the second half of the sentence separately, and then we combine them. So this is the image that the model sees, and this is the query image. This image is just an example I brought to show you one of the difficulties of the data set. These two images belong to two different classes, and this image seems to be from the class that is the closest to the class of this original image. So this image is classified as crested auklet because of these properties, and it is not a red-faced cormorant, the class of this image, because it doesn't have a long flat bill, and this long flat bill property is decided to be uttered in the sentence because it has the lowest score. It is one of the properties of this class that has the lowest score when it gets projected to this image. So now, of course, you might think that to be able to generate such sentences or such explanations, we need annotations, we need annotated data sets, and this might be very time-consuming or expensive. So and also you might think that the sentences that are generated are not reflecting the decision maker's thought process. Typically, when you want to generate explanations that are faithful to the decision-making process, then you lose from the accuracy, which is not something that we want. So then the next question becomes, how can we generate explanations that are conversational, that are easy for the user to understand, and also that reveals partially maybe the thought process of the actual decision maker. And here we implemented language as a bottleneck of the decision maker to reveal a bit of the thought process. So again, there is a game that is played between, this time, two different agents. And the first one doesn't have access to the data. It doesn't see the image, but it has ability of language. So it can ask questions about its own, to verify whether its own thought is going into the right direction. So, so the first agent thinks in this example that this image might contain a cat, a dog, a car, or a plane. Now he is unsure which one is present in the image. So it needs to come up with a question that could eliminate at least half of the classes after revealing the answer. And the second model is able to look at the image. It is able to answer any question that it is being asked, but it is not allowed to answer every question. It can only answer the question that it has been asked. So now the question is it furry? The second agent says yes, that eliminates two of the classes, that leaves two classes, and that determines the next question. Does it have whiskers? The model says no, and then one of the classes gets eliminated again, and the decision has been made. It's the dog. So very briefly, how this model works is we have two agents communicating with each other, and the first one has an extended memory mechanism that is implemented with an LSTM. And the hidden unit activations of the LSTM enter a multi-layer perceptron that predicts the next question. Actually, it predicts the attribute that determines the next question, the attribute that maximizes the accuracy to the final decision. And in this case, this could be whiskers. Does it have whiskers? Now, the second model has the perception module. So an image enters a classification framework. It could be ResNet, and then the last, I show the last two layers of this that network. This could be an MLP, and these two these kind of ends of the model shows a binary decision for the corresponding attributes. So furry, whiskers, black appears also here because we trained this with using attributes. And as you can see, the model actually has answers to all of the questions, but it is not allowed to reveal it. It is allowed to reveal only the answer to the second question, and that determines in this case, the end of the game. So in which cases this kind of decision-making mechanism could be useful? Let's say we are looking at two images that seem to be quite similar. We don't know if they belong to the same class. We don't know which class they belong to. Now we ask questions whether the object in these images have white underparts. It seems they both do, and they fall into the same bucket. That eliminates some of the classes. The next question is determined by the remaining classes, and this is not solid breast pattern and so on. At some point, these two images fall into two different buckets. And the question that determines this split is black wings. The first image doesn't contain an object that has black wings, and the second one does. So the second one gets classified into a green kingfisher, and the first one gets classified into a blue kingfisher, which is the wrong decision for this image, actually, because these two images actually belong to the same class. But as you might notice, the black wings of this image is really not visible because the bird is flying, and this was the reason why the classifier made a mistake. Another example may indicate also the difficulty of the dataset, where two images, actually in this case, these two images belongs to the same class, but they differ a lot visibly because they are two different genders of the same class. The black-headed one is a male bird and the other one is a female bird. And naturally, maybe, the first image gets classified incorrectly because the classifier has learned to look for these kind of spurious correlations in the image. The most distinct property of this class, it thinks, is the black crown, which is not visible in this image. So it classifier makes this mistake of classifying this image into the wrong class. Now, we might not even have access to attributes. Then how would we achieve a similar task? We thought we need to simplify the problem, and we looked at human sketches. And so here the aim is to come up with properties that are common to these objects, that everybody would agree that a face needs to contain these 3-4 different properties, and all of the other details are kind of the artist specific, which are not important to classify these images correctly. So we are searching for these properties, and these are not necessarily nameable. So we thought we could come up with a universal vocabulary, a restricted vocabulary of 7 different characters of geometric shapes, and we can represent all of the classes in these sketch data sets using those 7 primitives. Our primitive matching network is trying to do precisely this, regenerating the image such that the components that are visible in the image are going to be only among these 7. Then we can eliminate all the details that don't kind of appear in all of the instances of this object, and we can conclude that a face contains 2 eyes, a mouth, and a circle. And what would be one use case for this? An dialogue-based game that may look like this. 2 agents are playing this game with each other. The first one starts drawing until the second one can predict the class of the image correctly, like Pictionary. So we are aiming for this kind of compressed communication. Then briefly, how we achieve that is, so we take the sketches that are, these data sets are available online, and we split, and these data sets also have the information that contains when a certain, so how the artist draws the image. First comes what component, second comes what component, and so on. So based on that, the sketches can be splittable into primitives already. And so we take these one by one split primitives, and we also take our drawing primitives, our vocabulary, and we feed these 2 into what we call a stroke encoder. This is just a simple neural network that gives us embeddings, vectorial representations of these 2 pictures, basically. And then we take these and then we try to find correct affine transformations of the drawing primitives that could match the sketch part that we are looking at the best when they are oriented differently. Then the next step is to render these transformed primitives and the original primitives into the same coordinate grid. there we can compute distances between these two, or a set of primitive renderings and the rendering of the original primitive. This gives one component of the loss function that we optimize. The second part of the loss function is what we call compatibility function, where we just the original orientation of the primitive, we try to find the compatibility between that and the primitives that are extracted from the sketch. And we optimize these two losses simultaneously. Some examples. So these are different like chair, cat, and fire track classes in this data set. And our model with 10% budget draws these primitives. Then with higher budget, you can see, maybe you can identify some of the objects better. Then with 30% budget, it looks like this, and with 100% budget, it looks like this. So somewhere in between these two, for example, in the case the cat, maybe we don't need so many details for the fire truck. The next work I would like to share with you is it goes a little bit further into the direction of vision language models. Those frameworks that are able to generate sense about a given image. And what we would like to do in this work is to transcribe, in a way, what different vision feature backbones have learned. What does it mean? We would like to use vision language assistants, vision language models, to determine for this point in the image, what would, let's say, ResNet layer 39 things is present. It says the most beautiful girl in the world in this case. And then we also would like, within the same framework, to point to the evidence for different words that could appear in a sentence, like girl appears where in the image, smile appears where, and so on. To achieve that, we take the vision encoder of a vision language model. This could be CLIP, for example. This could be ResNet, and it's a vision encoder. And so we have these feature maps that we would like to basically decipher, transcribe. Now, from every layer, we can take these maps, and we introduce dropout to add some randomness. And then during training, we drop these and we pool these features, and we feed those into a model, a language model that has been frozen, that has been pre-trained, that could translate these features that have, like some of the features that come from the feature map, and some of the features that come from the pooled regions. And this is the part that we train. The translation is the part that we train, and the language model is frozen. The language model is able to tell us sentences like a young girl eating pizza in a restaurant, and it is able to do this because these data sets, for example, MS COCO, contains sentences, paired data with sentences and images. Then during the inference time, now we can specifically ask for different noun phrases or different words that appear in the sentence. For we can ask the model to tell us what is the region in the image where this appears the most, the most salient part of the image where this object appears, based on these probability scores. So what we have noticed is, by doing this, the model, first of all, the higher levels of the model, the deeper the model gets, the more details about the object the model can mention. The shallow parts of the network mentions only patterns, for example. One example is the layer 21 says abstract geometric pattern with a black and white stripe for this location. Layer 39 says a zebra in the black and white striped pattern, a close-up of a zebra. It says the higher levels of the network. And then if we want to name these regions or point to where zebra is, according to the layer 49 features, it points to these regions and so on. We see that the model makes different decisions or mentions different properties, different objects based on which level of the model we are asking the question. So in a way, in this work, we were trying to decipher what the model has could be thinking about. Of course, I can show you a lot of visual examples about this, but it is very, I mean, if not impossible, to evaluate this in a quantitative manner. This was one of the reasons why we had a difficult time with this paper. Yeah, so this is one more example for different patterns, different for the same image, different words that are being mentioned based on the regions that the model looks at. So this is one paper that maybe is a little bit further from my explanation argument, but it is, I find this kind of applications also interesting, and it's somehow in line with vision language-based explanations. So the task is we take an image and then we combine it with a sentence that would potentially manipulate the contents of the image such that it shows these properties now. And this is achieved by a frozen vision language assistant. In this case, we don't generate images, but we look for we retrieve the image that has the highest the highest match with this image and this sentence together. So, so this is the input image. This is the text modifier. We feed the image into a frozen image captioner that gives us a sentence that talks about the contents of the image. And then we take this sentence and then we convert it into a prompt. We feed that to a large language model together with the sentence that comes out of the image. And then the large language model now generates a sentence that contains the properties of this sentence and this sentence together. So it generates another sentence that contains the properties of this image and this sentence. Then we feed this sentence to a text encoder, and from the image database, we feed all of the images into a visual encoder, and we search for the image that has the highest information content based on this sentence. And although there is no training of the models, of any of the models here, just by using frozen language models, frozen image encoders and visual encoders, we are able to retrieve a very highly similar image to the sentence, actually. And that was the whole point of this paper. Some examples. So taking this image, giving this instruction, we retrieve this image. So for example, for counting and zooming. This is the original image with 4 men wearing red ties. The modification caption says it has to have only one person wearing the same suit. The photo size is zoomed in, and this is the retrieved sentence. So all this capability comes from of course, the large language model having been trained with very large scale data sets, but the fact that the large language models and vision language models can be reused in this way to achieve different tasks is very interesting in my opinion. Some failure cases. So, for example, if there's an ambiguity in the reference image, the description of the reference image says a person on a surfboard riding a wave in the ocean, and the instruction says the person needs to be shirtless, the photo has to have a darker background, and is a shot from a closer distance. Now, it is not clear what the person in this image is wearing, and so on. This is one difficulty that comes from the data itself. And the instruction is not very well aligned with the description that comes from the large language model. And then the large language model might be doing the wrong captioning. For example, in this case, pigeons sitting on a bench in front of a building is wrong for this image. And if the starting point is wrong, then the target is wrong, basically. And so in that sense, these are reasonable mistakes that the model makes. As a conclusion, learning abstract representations of the objects, in my view, can constrain the system for improved interpretability. I talked about the sentences that we generate for birds that were image specific and class specific. Then I talked about the dialogue, the image reference game, in a way, where the model has to come up with the correct answer, the correct questions to ask to reveal the thought process of the model. And so I believe that these abstract representations, learning these abstract representations is an effective means for evaluating the conceptual understanding of the model. I will go into this very briefly in the next part of my talk, and this can help comparing different objects and assess similarity. I talked about the sketch-based primitive learning. Now, I mentioned that being able to communicate effectively, or being able to be sure that your generated explanation is useful for the communication partner, you need to understand the communication partner. And here we focus on that. The example is a simple game where the two agents look at the same images, the two images. And the first one is needs to pick one image, describe it, and the second one needs to, based on the description, pick also the same image. Now, there's a caveat. The second agent is colorblind. So if the first agent talks about colors only, which would be the most discriminative property, then the second agent won't be able to correct the image. And the only signal that this first one receives from the second one is whether the image gets correctly picked, or whether the correct image gets picked or not. Then over time, the first one understands that the second one is not able to understand colors and starts talking about properties that are not color-based. That helps the second one understand the question better. So we have a speaker-listener model that actually, from the perception side, is the same thing. So we give the two images to the same neural network here and here. And then the model predicts the attributes that correspond to these images. Then we contrast these predictions, and we say that for example, in this case, red beak is the most highly discriminative property. What happens if I communicate red beak property to the second agent? The second agent is not able to understand it because there is some form of noise introduced. All the color-related properties are blocked. Uniformly, randomly, I will choose left or right, or up or down. Then this rewards get communicated to the first agent that keeps track of all the gameplay. So this is again a memory mechanism that forms an opinion about the listener, about the communication partner, and based on that opinion, we are going to pick the next sentence, the next image. The next noun phrase. Some example games. The most discriminative property is here. The chosen property is given in the second row, and this is the game. These are the images that the models are looking at. In the first game, the first one mentions only the color-related properties, and the second one cannot correctly predict the image. And over time, the first one learns to understand what the second agent is able to or is not able to understand, and mention properties that are of interest to the second one. And finally, I would like to talk about this example that goes into a similar direction, where we were prompting large language models to pretend to be a certain character with some kind of restricted understanding of the world and describe an object. Like pretend to be a 4-year-old and describe what is black-footed albatross. And the model would say, it's a big bird, lives on the water. Then as a 4-year-old, describe cardinal, describe indigo bunting, and it would come up with indeed sentences that a 4-year-old could talk about, could mention. Then we take these sentences and we pretend that these are the ground truth information for the image, for one image that comes from this class. And we feed this into a vision language model that is trained to learn the correspondence between these sentences and the images. Now, this trained VLM at inference time, we can give any other example from these previously seen classes, and see if the model is able to predict the class correctly or not. Of course, if the sentence has a lot of details about the class and about maybe even the image, by coincidence, then this model is able to learn a better understanding of the class, the concept of the class, and can answer or can be very accurate. But if these sentences are very restricted, of course, this is going to be trained with a low baseline and it won't perform very well. But for the purposes of this work, what we are trying to see is whether large language model is able to impersonate, and what would be the effects of these, or how would these, or would there be some biases in the decision-making process if we feed the model with these information. So we tried, according to different age groups, like 2-year-old, 4-year-old, 7-year-old, 13-year-old, and 20-year-old, different vision language models, backbones, and we trained these vision language models with the sentences of these. The sentences are the same, the images are the same, the backbone differs. And we can see that some models perform better than others, but depending on the age group of the sentence, with the increasing age, the accuracy improves. This is as expected. Then we also tried different large language models and to see if their abilities of impersonation. And we have seen that even the non-proprietary models like Vicuna 13 billion is able to give us sentences that indicate that it can impersonate different age groups. Of course, in this case, ChatGPT was giving us better results. Some qualitative examples for a 2-year-old, for asked to describe a field sparrow, a bird species, and this car brand. We tried it in 2 different data sets. So it talks about much like primitive things, like it has feathers, it has little wings, I like to watch it. Then with a 4-year-old persona, it talks a little bit more about, it uses a more complex vocabulary. And we can see that with increasing ages, they talk about more and more details. And in the 20-year-old case, it also talks about, it could be something historical, it could be something out of what one can see in this image, for example, but what one can read from Wikipedia about these objects. Something interesting that we have observed was if we ask the model to pretend to be an ornithologist and car mechanic and talk about birds, that the model is able to perform better at bird classification if it pretends to be an ornithologist, and it gives better results for a car mechanic if it is trying to describe cars. That brought us a question: what would happen if we ask it to be a man or a woman and describe a bird or a car? And as we can see, that a man describing a bird performs less than a woman describing a bird. Whereas, on the other hand, if we ask, and this was vice versa in case of cars, and in this case, we are asking the model to be a black person and a white person and describe a bird, and some stereotypical kind of biases come out of the large language models that indicates that black person personation is not able to describe birds as well as a white person impersonation, which really doesn't make, which could also be worrying in some contexts, which may indicate that we need to work on these problems that large language models have. And so after having noticed this bias issues with large language models, we decided to look into it a little bit more detailed. And we decided to collect this data set with different faces and ask the model questions that have nothing to do with how a person looks like. Like, for example, is this person reliable for this person? Is this person hardworking for this person? Could this person be a hairdresser for this person? The ideal answer should be, I don't know, or yes or no, uniform randomly. But we have noticed that models actually have strong biases against genders.
Zeynep, sorry, can you hear me?
And this was our attempt to evaluate gender bias in vision language assistants. As I mentioned, we collected these data sets and we balanced these data sets based on gender and ethnicity, and we collected these additional sentence annotations, so to say, based on prior work and also ChatGPT proposals, and we came up with a list of properties that we call personality traits that we use in this query sentence. Does the image display a person who is, for example, reliable? And then this gets converted into an instruction, and the answer, this question is asked about every image in the data set, and the model needs to answer yes, no, or unsure.
Zeynep, can you hear me?
Sorry?
I'm sorry,
Am I running out of time? Sorry. I can wrap up quickly.
I'm really sorry.
With these primitive explanations for our understanding of the world. And I also talked about how developing explainable deep models is important for user acceptance. And in fact, understanding the mental model of the user is necessary for effective communication. In the context of medicine, what could be an important application for the research that we have been doing? A dialogue system like this, where the user is asking for a measurement, whether based on this measurement, am I healthy? The model needs to say not only yes or no, but also say, based on this evidence that I have found in the image, there's a possibility that this indicates diabetes. Depending on what the meaning of possibility is, of course, the user can take a different stand in this diagnosis. Then if the user is not an end user, but an eye doctor, then the expectation is that the model needs to talk about a little bit more details of the diagnosis, using more complex vocabulary that is more suitable for the communication partner. And if the user is an eye doctor, a specialist, then the vocabulary needs to be adapted to the needs of that user. Then, of course, if we are talking to a child, the vocabulary should change. Maybe the examples should change. Maybe some illustrations should be provided. If we are talking to a person whose only interest is to be able to reproduce what they see in on a plate, then the structure of the sentence needs to change. Depending on the type of the user, for example, showing or uttering only the diagnosis is not enough. In some cases, you need to also, the model needs to be able to give suggestions on what to do in these cases. Thank you very much for listening to me, and if you have any questions, I'm happy to take them.